Cool. Today in this video we're going to be taking a deeper look at transformations, including translations, so thinking about everything in homogeneous coordinates. If you haven't seen the previous video on homogeneous coordinates, I do suggest that you go back and take a look at that. But now let's take a look at how we can combine everything together. So, as a reminder, we're working with homogeneous coordinates, so we'll be reporting if we want to think about looking at coordinates in the plane. We're going to write out ordered triples. Looking at always the last coordinate will always be a non-zero number, and then we get unique coordinates for our xy coordinates by setting the last coordinate to 1. So our coordinates for plane type points look like that. If we're thinking about 3D points, we'll add one more coordinate here, and then, so really we're looking at length for vectors, always resetting, scaling so that this last coordinate is 1 gives us a unique point in 3D space. So, speaking of scaling but in a different way, if we do want to scale an image, scale the either plane or 3D space, we've already seen how to do that using transformations. Just multiply either by a scalar or by, without homogeneous coordinates, we'd be multiplying by, something that looked like C times the identity matrix. Here, of course, if I multiply something like my set of coordinates over here by C, if C is non-zero, that doesn't change anything in terms of the homogeneous coordinate, so I need to be a little bit more careful. So for a 2 by 2 matrix, if I want to scale by some vector C, I'd multiply my point x, y, 1. Again, convention is to use row vectors for graphics, but I can have my scalar here. Essentially, my matrix C times the 2 by 2 identity matrix is in this top left block. And then give myself 0, 0, 1 for the last row. That will give me something that looks like not a matrix of this form, but we will have C times x, C times y for the second coordinate, and then the last coordinate will just be 1. This truly would, if we then translate back just looking at the corresponding point in the plane, this would truly scale the x and y coordinates. If we're looking at 3D images, same idea. We'll have our scalar times the identity matrix. That's definitely not what I want. Scalar times the identity matrix there. And then the last row is just 0, 0, or last column is just 0, 0, 0, 1. And that does get me C times x, and then C times y, and then C times z, and then that last coordinate being 1 fixes the scaling in place. So we've got that idea. That is something that we could use to either dilate or shrink an image, either spread all points out. I don't know, like if we wanted to double the size of an image, we could use scalar 2, for example. If we wanted to shrink it by half, we could use 1/2. You probably, hopefully get the picture. We could do different things in different directions, like we could stretch by 2 in the x direction, and then keep the y direction constant by choosing different scalars over here. I will say, though, all of these scale about the origin. If you've ever zoomed an image, you know that it matters. You know whether I zoom over here versus somewhere over here. So we want to figure out how to zoom about some point other than the origin. So to change the center, the procedure, and this is going to be something that recurs throughout the video. If I want to zoom about some point other than 0, 0, so if I do head back up here, all this was expanding things outward from 0, 0. Right here. If we want to, for example, look at zooming in at the point 3, 2. What I want to do is move this point so that it's at the origin, do my scaling, and then move everything back so that my center is back at 3, 2. So we talked about moving the origin 2, 3, 2. We just add 3 to all x coordinates, 2 to all y coordinates. If we want to move 3, 2 to the origin, we need to do the opposite. So I'm going to take my point here, x, y, write it in homogeneous coordinates. What I'm going to do is move everything so that 3, 2 acts like 0, 0. So that means my bottom row that's doing the translating, I want to move my x coordinate x coordinates all left by 3, y coordinates all down by 2, and then everything else is as is. Then, say I wanted to shrink by, shrink to 80% in the x direction, and then 50% in the y direction. I would use my scaling matrix there, and then, as I said, now I need to move everything back to where it was. So I will do that with this translation matrix that moves what was now at the origin back to 3, 2. If I multiply that through, which I don't think I'm going to bother doing, that would get me a matrix that zooms in, or I guess actually this is zooming out, it's shrinking everything, but yeah, zooms out about the point 3, 2. Let me zoom back in, or zoom back to 100. So, for your exercise, I want you to create a matrix that scales the plane by 2 in the x direction and 3 in the y direction, still working in homogeneous coordinates in order to practice those. Okay, so that's scaling in homogeneous coordinates. Now we want to look at rotation and reflection. So again, without thinking about homogeneous coordinates, we've already talked about plane rotations, and we saw or could see that in order to rotate the plane clockwise by theta, we could use the matrix Q, where we're using, I guess, yeah, cosine theta, negative sine theta, cosine theta. Whatever angle you're planning to rotate things about, fill that in, get yourself some numbers. If, for example, you are using, like you want a 90-degree rotation counterclockwise, counterclockwise. Let me fix that. So, counterclockwise. So, we rotate the plane counterclockwise by pi over 2. We would need to substitute in pi over 2. We would, in fact, get our 0, negative 1, 1, 0 matrix that we've already essentially formed by hand. So, that is that. Now we want to look at what happens in homogeneous coordinates, and really, it's not going to be too different from this original matrix here. We're just going to fill in. So our cosine theta homogeneous version. Sine theta, cosine theta, and then our column 0, 0, 1. So we've got that. We could extend to rotations in higher dimensions. Here, we need to think a little bit more about how to configure our various sines and cosines depending on how we want to rotate. It'll be easiest, the types of rotations that we'll be thinking about we'll mostly focus for this video at least on ones that keep one axis like X, Y, or Z fixed and then rotate the other two, in which case we just leave the corresponding entry in the matrix fixed as like 1 and then fill in these elsewhere. We'll see an example of that later on. For now, let's move on to reflections. So, if we want to create a matrix that reflects points in 3D space across the plane y equals 0, so if I draw a quick sketch of that, plane y equals 0 would be right here. So if we want to sort of make ourselves a mirror there, whatever point we've got over here, we'd want that to show up over here on the other side. We want to make then y equals 0. That's the plane x equals 0. Ignore that. So y equals 0. That plane would look something like that, the x and the z are free to be whatever they want. If we want to reflect a point then over here, somewhere over here, we would make our y-coordinate negative. So, in the familiar coordinate system, if we want to make y negative, we would do that. Homogeneous coordinates, we just fill in our our column 0, 0, 0, 1, and then leave everything as is. If I give myself some coordinates like this, then multiplying through, I really do end up with x, negative y, z, and 1. So that worked out. We could use similar principles to reflect across x equals 0 or z equals 0, reflecting across a different plane gets slightly more complicated, but we could fill that type of detail in. If you want to reflect across a plane that's not centered at the origin, we need to shift some things. So if we look at this next question here, I want to create a matrix that reflects points in the plane across the line x equals 3. Here we're just looking at xy plane to make things simpler. So we've got our line x equals 3 here, which is serving as our mirror. So if I had, like, I don't know, the point 2, 2, we'd want that to become 4, 2. So again, our strategy is going to be to move the line x equals 3 over to the origin. So that would mean shifting all coordinates left by 3. So if I create the matrix that does that, so we'd want to move left by 3. We're going to use a translation matrix, 0, 1, 0, -3, 0, 0. Reflecting then, it'll be across a vertical line, so we want the x coordinate to reflect. And then we shift everything back by translating right by 3, adding 3 to the x coordinate. Let's check that out. We had said that, again, our point 2, I'm calling this, should become 4, 2. So let me try that out. A homogeneous version would be 2, 2, 1. And part possibly of the reason that we write our vectors as row vectors, again, is so that we can, as we're layering on later transformations, we can write them to the right as we're used to doing. So if our input point is 2, 2, 1, shifting it here would be -1. Again, I keep on drawing this as a matrix instead of a row vector. -1, 2. And that should be a 1. One. Multiplying the row by this first matrix. 0, 1, 0, 0, 0, 1. 1, 0, 0, 0, 1, 0. 3, 0, 1. Then multiplying by the next matrix, this will become 1, 2, 1. And then finally, I add 3. So this does in fact become 4, 2, 1, which, if we're just focusing on the x and y coordinates, give me the point 4, 2 that I was hoping for. Okay, got one more example. Want to create a matrix that rotates points in 3D space, 30 degrees counterclockwise about the z-axis. So here, if we've got XYZ plane, we want to rotate in, so this direction about the z-axis, so our rotation would look something like this. We want the z-coordinate of our point then stay the same. So I'll fill things in. Homogeneous coordinates. Our last column is always going to look like this. I want my z-coordinate to stay as is, so I'm going to just leave that. And then for my x and y coordinates, I'm going to be using my cosine theta, negative sine theta, sine theta, cosine theta. If I want 30 degrees counterclockwise, theta is going to be pi over 6. So we can fill that in. Cosine of theta then is going to be root 3 over 2. Sine theta is going to be negative 1/2. We'll have a 0 there. That's not really going too far. I'm just not leaving myself enough room. So we'll have then for this last row of my 2 by 2 matrix, 1/2 and 3 over 2, and then fill that in with the 0. So that does the reflection for x, or sorry, the rotation for x and y. Leave z as is, and that would be our final matrix. So for your exercise, I want you to create a matrix that reflects points in the plane across the line y equals -2. One can also think about, we have our last type of transformation, which is projection. This is particularly interesting, for example, if you're developing graphics, you develop something with 3D type information, but then you want to project to 2 dimensions in order to know how to display it on a screen. So there's definitely a lot of interesting stuff there. I would redirect you to the textbook section on graphics for more information about, projecting to either a plane crossing through the origin, or what the textbook calls a flat, something that doesn't cross through the origin. Getting that information, seeing how to do it in homogeneous coordinates, using these same ideas of translating something that isn't at the origin to the origin. So enjoy and take a look at that.